any two m by n matrices A and B, the following statements are equivalent. First, B is obtained from A by applying the column operations. Second, there is a non-singular matrix Q such that B is equal to AQ. Third, column spaces of A and B are equal. Fourth, column echelon forms of A and B are equal. We have to show that all these statements are equivalent. That is, to obtain second statement from the first one, third from the second one, fourth from the third one, and first from the fourth one, right? So we have already done this proof for the row spaces and row rank of the matrix, and now we are going to prove this theorem for the column space and column rank of the matrices. Before starting with the proof, let's go through this remark, a very important one. If A and B are two matrices of the same type such that column space of A is equal to column space of B, then column echelon form of A is equal to column echelon form of B, right? Where AC and BC are the column echelon forms of A and B respectively. So what we have concluded from this, that if C is obtained from A by applying the column operations, and if D is obtained from A by applying the column operations, then column echelon form of A is unique. That is, then C is equal to D. This is the result, and I am going to use this result in the proof. So let's start with the proof. So first we obtain the second statement from the first one. What is the first statement? That is, B is obtained from A by applying the column operations, right? That is elementary column operations, right? Suppose that corresponds to post multiplication by the elementary column matrices. That is, let's say we obtained the first elementary column matrix as F1, then I obtain F2, then by further applying the column operations I obtain F3, so on, right? Let's say F1, F2, F3, so on. These are the elementary column matrices. So because we have applied the post multiplication, so therefore B is equal to, because B is obtained from A by applying the column operations, so B is written as A multiplied with F1, F2, F3, so on up to Fr. And let's denote this multiplication of matrices as Q. So B is equal to AQ, where Q is equal to F1 multiplied with F2 multiplied with F3 up to Fr. Now as each of these F1, F2 up to Fr, these are non-singular matrices, right? So since F1, F2, F3 up to Fr are non-singular matrices, and because their multiplication is equal to this Q, so therefore we say that Q is also non-singular matrix, right? So we have shown that there is an existence of the matrix Q which is non-singular such that B is equal to A multiplied with Q. So we obtain the second statement, that is B is equal to AQ from the first one. Now to obtain the third statement from the second one. So what is given to us in the second statement? Suppose there exists a non-singular matrix Q such that B is equal to AQ, and we have to show that column spaces of A and B are equal. Now as there exists a non-singular matrix Q such that B is equal to AQ, so therefore column space of B is equal to column space of A into Q, right? And because Q is a non-singular matrix which is further equal to column space of the matrix which is multiplied with the non-singular matrix, right? This is a result I have used over here. Reason: Q is non-singular or invertible, right? So this implies column spaces of both the matrices, that is A and B, are equal, right? Now to obtain the fourth statement from this, suppose column spaces of A and B are equal, and also since A in column echelon form is obtained from A by applying the column operations, and B in column echelon form is obtained from B by applying the column operations, and also it is given to us that column space of A is equal to column space of B. So therefore, that is the remark we have read before the start of this proof. Whenever this happens, we say that these two are equal. That is, the column echelon form of A is equal to column echelon form of B, where this AC and BC, these represents your capital C and capital D in the remark, this one, right? Alright, so now to obtain back the first result from this fourth result, suppose AC is equal to BC, that is the column echelon forms of both these matrices are equal, and since column echelon form of A is obtained from A by applying the column operations, column echelon form of B is obtained from B by applying the column operations. Whenever this happens, there exists a non-singular matrix. So let's say there exists a non-singular matrix P for this and a non-singular matrix Q for this result. So there exist non-singular matrices P and Q such that column echelon form of A is equal to AP and column echelon form of B is equal to BQ. Right? So this implies I can write this A as, because P is a non-singular matrix, so P inverse exists. So A is equal to, from this, P inverse column echelon form of A, which is further equal to, because it is given to us that column echelon form of A is equal to column echelon form of B. So writing here column echelon form of B for this column echelon form of A and multiplying this P inverse. This is further equal to, what is column echelon form of B? This is B into Q, right? So this is B into Q into P inverse. Let's take this QP inverse together. So this implies A is equal to B into QP inverse. Because P is non-singular matrix, its inverse is also non-singular and Q is also non-singular matrix. So their product is also non-singular, right? So from here we write that B is obtained from A by applying the column operations. Reason as QP inverse is non-singular. This is a result, right? Hence, we obtain the first statement from the fourth statement. So, we have shown that all these statements are equivalent, right? Okay, thank you. Stay blessed.